Hello everyone. In this video, we will use machine learning models in order to find out if a given news is fake or not. So this is called as a fake news classifier project. And the aim of the project is to build a fake news classifier using natural language processing. So as you can see over here, before we begin, we have to do some necessary imports. And over here, we have imported NLP utils. So what NLP utils does is that it offers us a set of APIs to work on strings such as names, sentences, paragraphs, and tokens, which are actually represented as an array of strings or words. And then we have pandas. We have imported pandas, and pandas will help us to create data structures. And not only creating data structures, but pandas also help us to manipulate those data structures, and we are going to read our dataset with the help of these pandas. And then we have imported Seaborn, and Seaborn will help us to visualize statistical graphs. So Seaborn is basically a data visualization library which is based on Matplotlib. And then over here we have imported train test split. So train test split is something that we will use in order to divide our dataset into training and testing parts. And after we divide our data set into train and test, we use our machine learning models. And then over here, we have imported count vectorizer and TF-IDF vectorizer. So we'll use both the vectorizers to see which model has performed well. So what count vectorizer does is that it provides us a simple way to both tokenize a collection of text documents and build a vocabulary of known words. So this is what a count vectorizer does. It will encode new documents using that vocabulary. And then we have imported TF-IDF vectorizer. So TF-IDF stands for term frequency and inverse document frequency. So this is a very common algorithm again to transform text into meaningful representation of numbers, which is used to fit machine learning models for our predictions. And as you can see over here, we have read the data using pd.read underscore CSV. We have used this read underscore CSV as the data set is in a form of a CSV file. And over here, you can see that the data set is called as train.csv. And once we have read the data, we have loaded the data, and you can see over here that we have columns over here like the ID column, title, author, text, and label. So the label column over here is our target column, and 0 means that the given particular sentence is not fake, and 1 means that the particular sentence given is fake. And so basically this is the label column, which is nothing but our target column. So let us go ahead and do some data understanding. So first things first, we will see how many rows and columns are present in our data set, and we have used a function called as df.shape. What this line will really show us is that it will display us the total number of rows and columns present in the data set. And as you can see over here, we have 20,800 rows and 5 columns. And the fifth and last column is our label column, which is nothing but our target column. And then over here, what we have done is this line of code, what it really does is that pd.set option display max call with will display the entire column. I mean, all the information in that particular column will be displayed to us. And as you can see over here, the df.title over here did not show us the full line. But once we use this option, which is called as the set option and display max call with, we can see the entire text or title in that particular column. And then over here, this is our text column. So as you can see, title contains the headline of the news. So the title is just the headline, whereas the real news is in the text. Whereas as you can see, text contains the information regarding the headline. And this is the headline, and this is the complete news about that headline. And then we have used a value underscore counts on the target column, which is our label column. And as you can see over here, using the value underscore counts, we can see the total number of elements present in that particular column. And the number of ones is 10,413, The number of zeros present in that column is 10,387. And to check out if there are any null values in this particular data set, we use a function called as df.isNull.sum. So what this code will display us is that it will display us the total number of null values present in our data set. So as you can see over here, there are a few column names like the title, author and text. So these three columns have some numbers shown in them, which means that in the column title, there are 558 missing values. And in the author column, we have 1957 missing values. And in the text column, we have 39 missing values. So df.isNull will show us the total number of missing values. And when we have these numbers as 0, that means that there are no null values present in our data set. And the next thing that we have done over here is that we have directly dropped the null values. So wherever we had NA values, we have dropped those NA values using the df.drop NA. So the null values were removed using the drop NA function. And after that, as you can see over here, we have again used the same line of code, which is the df.isNull.sum. And as I told earlier, we can see that there are zeros. That means there are no null values present in our data set now. And this data frame has no null values now, so we can go further. And what we have done over here is we have set an index, and as we can see in the output, the series.reset index function has reset the index of the given series. So this is our data frame now. And the reason why we see these cells, the reason why we can see such huge cells now is because we use a function above called as the max width. We use this code which said ped.set option. That's the reason why our data frame is now looking so big. And then let us go ahead. And the next thing that we have done over here is we have imported another library like the RE. So we have imported RE, which is nothing but the regular expressions. So regular expressions are nothing but they are a special sequence of characters that help us find or match other strings or a set of strings. And then we have imported strings. Then this is the text cleaning part. So the particular columns, text and title have some uh, symbols in them like special characters. So these special characters, as you can see over here, we have the addition character over here. So these special characters and alphanumerics have to be removed and the data has to be processed. And as you can see over here, this code will find out if there are any alphanumeric values. So alphanumeric values are nothing but they are numbers with letters attached to them. So we have used the lambda function, and as you can see here, we have used the slash w. These are nothing but this will find if there are any words and digits attached together. And then we have found the lower, we have converted the text into lower case, and we have used the lambda function again and converted the entire text into lowercase. And then the next thing that we have done over here is that in these text column, you can find out that there are some slash n. So this is but nothing but a new line. So we have removed those slash n's and replaced them with the empty place. That's nothing. We have removed these slash n's in using this particular piece of code. And then the other thing that we have done is we have removed non-ASCII characters. Again, we have used the lambda function and removed all the non-ASCII characters. And then we have mapped these lambda functions and removed the entire special characters from that particular text column. So what we have done so far is that we have removed the alphanumerics and then converted the text into lowercase, and we have removed the slash n's and we have replaced them with a white space. Okay, this is the white space. And then we have removed all non-ASCII characters, and then we have mapped it on our text. So in the end, this is our cleaned data. As you can see, there are no special characters in this particular data set now. And next thing that we have done is we have removed stop words and we have stemmed the data. So when it comes to stop words are nothing but words which add no meaning to the particular sentence. And the words, even when removed, have no change in the meaning of that particular sentence. Like there are a few words like the, is, or, for. Such words are called as stop words. And even though we remove these words, they do not change the impact of our sentence or the meaning of our sentence. So let us read this piece of line. And over here, we can see that in natural language processing, useless words or data are referred as stop words. And a stop word is a commonly used word such as the, a, and, in that a search engine has been programmed to ignore, both when indexing entries for searching and when retrieving them as a result of a search query. So as you can see, we have removed these stop words, and we had imported a few libraries again, which is nothing but our stoppers and port stemmer. So we have imported them, and over here we have used a port stemmer. So stemming is something where we change the word into their root form. As you can see over here, we have imported stop words from nltk.corpus, and we talked about stop words earlier. The other thing that can be seen here is that we have imported port stemmer for stemming, and port stemmer or port stemming algorithm is nothing but a process for removing the commoner morphological and inflectional ending from words in English. So it is the port stemmer that we are using, which will convert a word back to its root form. And as you can see over here, we have created an empty list called as corpus, and the entire text that we have above has been lowercase, and then these words after stemming will get appended in the corpus. And as you can see, the next thing that we have done is that we have created a split in the data frame. So we basically converted our data frame into train and test. And before converting the data into train and test, as you can see, we have divided it into independent and dependent variable over here. And as you can see, we have taken the label on y, which is nothing but our target column. And this is how the target column looks like. And this is the y dot head. And after we converted our data into independent and dependent, the next thing that we have done is that we have converted the data into train and test. So as we remember, we had imported train test split. This is the code related to that import. And as you can see, we have taken the text on X, and we have taken Y, which is nothing but our target column. And then you must notice that we have a test size, which is 0.30. So this test size indicates that around 70% of the data is going to be used for training purpose, and 30% of the data will be using for test purpose. And as you can see, if we change the number from 0.30 to 0.20, then our training data will be having a size of 80%, and then 20% of the data will be used for testing purpose. And then we have used a random state, which is 40. What this random state does is that let's say five people use the same machine learning model, among which two people use the same random state. Then these two people are going to get the same results. And then as you can see, we have split the data into 70% train and 30% test. And the next thing that we have done over here is we have applied vectorizers on our text column. So the we have used two vectorizers. One is the TF-IDF vectorizer, and then we'll apply our machine learning models on this particular vectorized data. And then we apply the same machine learning models on the count vectorizer to see how the accuracy changes. And for now, as you can see, the TF vectorizer uses a simple example. DTF IDF vectorizer will tokenize documents learn the vocabulary and inverse document frequency weightings, and allow you to encode new documents. Alternately, if you already have a learned count vectorizer, you can use it with a TF-IDF transformer to just calculate the inverse document frequency and start encoding documents. So the TF-IDF vectorizer over here has been applied on the Xtrain and Xtest, and this is the TF-IDF test over here. The next thing that we can see over here is that we have the TF vectorizer names. We use the get feature names, and at the same time, as I told earlier, we have used count vectorizer along with the TF-IDF vectorizer. And as you can see, the count vectorizer provides a simple way to both tokenize a collection of text documents and build a vocabulary of known words, but also to encode new documents using that vocabulary. So this is our count vectorizer. As I said earlier, the count vectorizer provides a simple way to both tokenize a collection of text documents and build a vocabulary of known words, but it also helps us to encode new documents using that vocabulary. And over here, these are the count vectorizer. We use the get features function. And as you can see, these are the feature names. And let us move ahead with the machine learning part. So when it comes to machine learning, we have used some models like the Navy Bayes model and the Navy Bayes classifier over here. So the Navy Bayes classifier is a collection of classification algorithms which is based on the Bayes theorem. It is not a single algorithm but a family of algorithms where all of them share a common principle, which is nothing but every pair of features being classified is independent of each other. So over here we have used this Navy Bayes model or the Navy Bayes classifier, and we have used this model on the TF-IDF vectorized, and this is the TF-IDF vectorized Navy Bayes classifier, and we have used a multinomial Navy Bayes, and to evaluate these models we are using something called as metrics, and the metrics that we will use to see how well our model is predicting, we are going to use the accuracy score. So the accuracy score will be compared with other models in order to see which model performed well. And at the same time, we are going to use something called as the confusion matrix. And confusion matrix is another evaluation metric which can be used to find out how well our model is performing. And we can find out the total number of wrong predictions made by our model with the help of the confusion matrix. And as you can see over here, we have used this multinomial Navy Bayes, and we have fit this model on the TF-IDF vectorized uh, model. We are using this model on the TF-IDF vectorized, and then we have fit the model on TF-IDF train and Y-train, and then we are using this model to predict on the TF-IDF test. So we are predicting the model on train and test, and then we use the accuracy score, and over here we have printed a confusion matrix. So as you can see over here, the accuracy score for this model is around 77%, and then we used a confusion matrix, and then in order to evaluate how many wrong predictions the uh, Navy Bayes model made, we use the calculations from the confusion matrix, and as you can see over here, the wrong predictions made by our model is 1251 out of 5486, and then the percentage accuracy, as you can see over there, is 77%. The next thing that we have done over here is that we have plotted this confusion matrix, and we used a heat map, and as you can see, this is our confusion matrix. And then we have applied the same model again, but this time we have count vectorized, and previously we used the TF-IDF vectorizer, and this time we are going to apply the same model which is nothing but our Navy Bayes model, and we will apply it on the count vectorized data. And as you can see, we have used the same multinomial naive Bayes, but this time we have used the count train. Then we have predicted the model on the test as well as the train, and then we have used the similar evaluation metric over here, which is nothing but our accuracy score. And then we have printed the confusion matrix, and as you can see over here, this time the accuracy is 90, and previously the accuracy using the TF-IDF was 77. So we can say that the count vectorized model is performing well as compared to the TF-IDF model. And as you can see, we have our accuracy as 90, and this is the confusion matrix. And then out of this confusion matrix, after doing the calculation, we can see the total number of wrong predictions made by the multinomial naive Bayes using the count vectorized model. And as you can see, this time we have only 531 wrong predictions out of the total predictions being 5,486, and previously the total number of wrong predictions is 1,251. So we can say that the count vectorized model is performing well as compared to the TF-IDF vectorized model. And then we have plotted the confusion matrix in a similar way. We use the heat map again, and after that we have used another model which is nothing but our random forest classifier, and we have imported this random forest classifier from sklearn.ensemble. And a random forest is a robust machine learning algorithm that can be used for both regression and classification tasks. When it comes to regression, we use a random forest regressor, and we can use the random forest on classification models as well, or classification use cases. And as you can see, we have done a similar thing. We have our TF vectorized model, and then we have the count vectorized model. So let us see how the model works on TF IDF vectorized model. So as you can see, we have used the random forest classifier on TF IDF train as well as TF IDF test. Over here, we have used a print command. So the print command will print the accuracy, the model accuracy on train, and then we have done the random forest models prediction on test, and we have printed the model accuracy on test as well. And then over here you can see that we have used a print command. What this line does is that it will draw a dotted line which will repeat for 50 times. And then we have plotted a confusion matrix, and we have printed the total number of wrong predictions made by this confusion matrix. And over here we have calculated the total number of wrong predictions made by the model. And as you can see over here, we have a model accuracy on train which is 99%, and the model accuracy on test is 90. And this is our confusion matrix over here. And let us see the total number of wrong predictions. Here the model has shown us that the total number of wrong predictions are 524 out of 5,486. Let us compare. So here we have 524 wrong predictions, and over here we have 531 wrong predictions. So this means that the random forest model has performed well using the TF-IDF vectorized model, giving us a total number of 524 wrong predictions out of 5,446 predictions. And let us use the same model on count vectorized model and see if there is any improvement. And as you can see, we have used the same model again. We have fit the model on train and test, and over here we'll print the model accuracy on train, and then we'll print the model accuracy on test after we print the model on test. And again we have used the same print command over here, which will draw a line. And then we have used the confusion matrix, and then we have calculated the total number of wrong predictions from this confusion matrix. And as you can see over here, this model performs similarly to the TF-IDF vectorized model, giving us a 99% accuracy on train and 90% accuracy on test. And over here we can see that this is our confusion matrix, and we printed our wrong predictions. So we can see that the total number of wrong predictions here are 521 out of 5486. So previously the total number of wrong predictions were 524, and now we have a total number of wrong predictions as 521. This means that the model is performing pretty well so far, and we can go ahead with the count vectorized random forest classifier. This combination has given us less number of wrong predictions so far, as the previous model gave us 524 wrong predictions, and again the previous model gave us 531 wrong predictions, and again the Navy base on TF-IDF vectorized model gave us 1251 wrong predictions. So we can say that so far our random forest model on the count vectorized data is performing very well. And then after using the random forest model on count vectorizer as well as the TF-IDF vectorizer, we have used another model, which is our KNN model, or the K nearest neighbors. So we have imported K nearest neighbors classifier from sklearn.neighbors. And when it comes to K nearest neighbors, KNN algorithm is one of the simplest classification algorithm, and it is one of the most used machine learning algorithms. KNN is a non-parametric lazy learning algorithm. As you can see over here, we have used the k-nearest neighbor, and we have fit this model on the TF-IDF trained or TF-IDF vectorized model. And as you can see, this is the model's prediction on train, and then we have printed the model accuracy on train, and after that we have predicted the model on test, the TF-IDF test, and we have printed the model's accuracy on test as well. And as you can see over here, the model accuracy on train is around 51%, and the model accuracy on test is 48. So far, this is not a very good model, because the other models gave us a very good accuracy. As we can see over here, our first model was Navy base, which gave us a 77% accuracy. So far, the random forest model performed very well, and the K nearest neighbors has not performed very well. And the other thing that we can see over here is that the TF-IDF model has not performed well as compared to the count vectorized. As you can see over here, every model has given us a less accuracy on the TF-IDF trained model. Over here, we use the confusion matrix, and as we can see, the model's accuracy was low. And over here, the total number of wrong predictions that we have taken from the confusion matrix is around 2817 predictions have been made wrongly out of total number of predictions, which were 5486. And let us go ahead and use the same model again, but this time we'll use it on the count vectorized model. And as you can see, there is a significant improvement as compared to the TF-IDF model. Over here we have done the same thing again. We have fit the k nearest neighbors model on the count train, and then we have predicted the model accuracy on train, and then we predicted we printed the model accuracy on train, and then we have predicted the model on test, and then printed the model accuracy on test as well. And as you can see over here, the model accuracy on train is 78%, and the model accuracy on test is 73. And then we use the confusion matrix, and the confusion matrix over here has given us a total number of wrong predictions again, and this time the total number of wrong predictions is 1470 out of 5486. This time we have less wrong predictions as compared to this TF-IDF model, which gave us 2817. But so far the KNN model has not performed very well. The perfect model so far is the random forest classifier on the count vectorized model, which gave us a 90% accuracy on test, with the total number of wrong predictions being 521. And this model can be further hyperparameter tuned in order to check if there is any improvement. And but for now, this is it for this video, and hope you like this video, and until then, have a good day. Take care.